Hi, Dr. Wang here. Today we're going to work on this assignment called Transcription and Translation 5. This is a rather complex assignment. To summarize the question quickly, we start with 6 mutants. Those are E. coli mutants that are unable to grow without an amino acid called leucine. What's interesting is if genetic material from this mutant and this mutant, when combined, is going to produce an individual, an E. coli, that's capable of producing its own leucine. So how do we unpack this question? Before doing so, we need to review what an operon and biosynthetic pathway is. Bacteria, unlike us, often have to produce amino acids for themselves. So here, starting with simpler compound, it's converted through a biosynthetic pathway by a number of enzymes and eventually to leucine. And this is an essential amino acid that's required for growth. Those enzymes in the biosynthetic pathway are encoded by genes. What's interesting is in prokaryotes, those genes are often arranged in a linear fashion on the chromosome. So they're literally next to each other. They're turned on together and they're turned off together. So this is called operon. All right, so now let's look at the first scenario when we have mutations that disrupts the gene within this operon. So here we have 2 hypothetical mutants. So mutant 1 disrupts gene A, mutant 2 disrupts gene B. So if we look at the genetic makeup of those mutants, because mutant 1 disrupts gene A, so it has no gene A, but it should have a functional gene B. Similarly, mutant 2 has no gene B, right? Because it disrupts gene B, but it should have basically a functional gene A. So when you combine the genetic material from mutant 1 and mutant 2, right? So when you put everything together, what you see is that this combined individual, this E. coli, actually has both gene A and gene B, which means this pathway goes on as normal, and then it's going to allow this combined new individual to produce its own leucine for growth, right? So here this combination basically will lead to growth. So now we're going to look at a second scenario where these 2 mutations disrupt the same gene. Over here, now both mutant 1 and mutant 2 disrupt the same gene, so gene A. So if I draw the connection here, mutant 1 should have basically no gene A, right? So, and the mutant 2, because it disrupts the same gene, also has no gene A. So when you combine these 2 individuals' genetic material, the resulting product or the resulting individual is an individual that has no gene A, which means this biosynthetic pathway will be disrupted right here, right? So, and then which means that this individual cannot produce leucine, and then therefore no growth, right? So the result of this is no growth. So I'm going to draw a connection from this combination to growth and to say that this is basically cannot. All right, so now we can come back and to look at the actual data. So when we look at this table, for example, if we take Lu061 and combine that with Lu201, the result is no growth. No growth is basically scenario 2. It means these 2 mutations disrupt the same gene. So basically, I can place these 2 under the same gene. So for the first question, basically you're going to go through this table and group the 6 mutants into groups like this. So a group, which is basically a gene, could contain 1 mutation, 2 mutations, or perhaps 3 mutations. And then once you're done with this grouping, basically the number of groups you have is basically the number of genes that are present in this operon. And then question number 2, which mutations are located in the same gene. So this is literally your grouping will tell you which 2 mutations are in the same gene. So we're going to take a break here and come back to questions 3 and 4.